Hi all, today we are going to discuss measurement of power in three-phase circuits. So before going to the power measurement in three-phase circuit, first we should know what are the different ways in which the three-phase circuit can be connected. So three-phase circuit can be either connected in star. So star connection, how it will be moved. Let us assume the load is having three different impedances. So three different impedances I am connecting here. So these are interconnected like this. So this is one case, or this can be connected in another manner. How? So they can be connected in delta connection also. So broadly we can speak that the three-phase connection can be made either in the star connection or in the delta connection. So if you are going for the delta connection, how many ways will be there? Only 1, 2 and 3. There will be no neutral wire. That means this delta connection will have only one system, that is three-wire system. So here there is no confusion. But if you go for star connection, this star connection can have either three-wire system or it can have four-wire system. How the fourth wire will be there? If the neutral point is also taken, then in that case we will have four-wire system also. That means star connection, there can be either three-wire system or four-wire system. Delta connection, there is three-wire system. So based on how many wires are there, so it decides how many number of wattmeters are required to measure the three-phase power. So that is given by a scientist. So that is given by a theorem called as Blondel's theorem. So let us see the statement first. Then I will try to explain you in detail, and we are going to also see that what are the common doubts or mistakes the people generally do in power measurement. So Blondel's theorem, it states that if a network is supplied through n conductors, then the total power is measured by summing the readings of n wattmeters so arranged that a current element of a wattmeter is in each line and the corresponding voltage element is connected between that line and a common point. And the second case again he mentioned, if the common point is located on one of the lines, then the power may be measured by n wattmeters. So seeing the statement, it is a little bit of confusing. So let us see the diagram so that this will be clear to you. So let us see the case of three-phase three-wire system. Three-phase three-wire system, that means there is no neutral point. Let us take the example of star connection without neutral point, or you can take it as a delta connection. Delta connection anyway, neutral point will not be there. So in that case they are telling there are two possible ways, because here how many wires are there total? 1, 2 and 3. Total 3 wires are there. So in this 3-wire system, either we can measure with 3 wattmeters. So if you are measuring with 3 wattmeters, they are telling that in that case the current coil will be connected in the respective phases, and potential coil or the pressure coil, that will be connected between each phase and to a common point. There will be a common point. That means that common point is not related to these conductors. So it will be connected to this common point. So in that case, how many will be there? 3 wattmeters will be used. Or otherwise, if you are taking any one of the conductor or any one of the phase as the common point, so in that case only 2 wattmeters will be required. So you can see here in this case what will be there? The current coil is connected in any two phases. Then the pressure coil is connected between that respective phase and the third phase in which the current coil is not connected. You can see this pressure coil is connected to this point. So in this case, because total number of conductors are 3, so 3 minus 1, so 2 wattmeters will be required only. So, but if you go for 3-phase 4-wire system, 3-phase 4-wire system is possible in the case of star connection. So in that case, we have to count total 4, not 3. We should not take as 3. Total 4 conductors are there. So in this case, we have to go for minimum 3 number of wattmeters. Minimum 3 number of wattmeters are required if the neutral point is provided. That means there is a return path through the neutral. So in that case, minimum 3 wattmeters are required, or otherwise we can go for 4 wattmeters. So 3 wattmeters are required here. Using 2 wattmeter, we cannot measure the power in the case of unbalanced star connection with neutral point. Only if the neutral point is not available, then only we can go with 2 wattmeters. This thing you have to remember. Either we can go for 3 wattmeter or 2 wattmeter. But if there is 4-wire, always we have to go for 3 wattmeter if the load is unbalanced. Okay, the same thing I am summarizing here. This is a 3-phase 4-wire system. We are going with the second case what he has mentioned. That means total number of wattmeters will be n minus 1. Total 4 conductors are there. 4 minus 1, 3, because we are taking one of the wire as the common. You can see this neutral wire I am taking as the common. But in the case of 3-phase 3-wire system, you can see 3-phase 3-wire. So 3 are there. We are connected to some common point, some other common point. So in this case, 3 wattmeters are connected in 3 respective phases. Or other possibility is taking one of the phases as common, then 2 wattmeters are required. Here also 3 minus 1, so 2 wattmeters are required. This is about the Blondel's theorem. So let us check each one of them in detail now. First, starting with the 3 wattmeter method. So where this 3 wattmeter method is used, this is used for 3-phase 3-wire, or this can also be used for 3-phase 4-wire, either balanced or unbalanced system. In both these cases, we can go for 3 wattmeter method. So let us start with the star connection. After that, we will go for the delta connection. So star connection, I am just assuming that these 3 wattmeters are connected in 3 respective phases. Current coils are connected in respective phases, whereas the pressure coil is connected between the respective phase and to a common point. Here I am assuming the neutral point is not available to us. And we are going to prove that whether you connect this point directly to the neutral, that means the second side of the pressure coil is connected to neutral point if it is available, or it is connected to some outside isolated point n dash, both will give the same reading. That we are going to derive and prove it now. So for that, I am assuming the neutral point of the load is not available, and I am assuming the potential, because this n dash and n are not at the same potential, I am assuming the n is at a higher potential compared to n dash. That means I am taking that potential is Vn n dash. Whenever you are mentioning any voltage, the first term will be at higher potential compared to the second one. That means this indicate Vn n dash indicate what is the voltage of n with respect to n dash. Please don't confuse. So similarly, the voltage of the each respective phases I am representing by Van, Vbn and Vcn. So what is Van? Voltage at point A. Let us assume this is my point A. So this will be the voltage at this point with respect to the neutral. Similar is the case if you are taking this as, let us take for example C. This is the voltage at this point C with respect to neutral. Similarly, this will be voltage at this point B with respect to neutral. So generally the voltage is represented in the same direction as the current. That means it is represented like this. This is the arrow. So in this way also I can represent it. Anyway, to avoid the confusion, we will discuss this in the next topic, because there only confusion will be more. Here I don't want to confuse you more. So now the instantaneous voltage is across the pressure coil of the wattmeters. So that I can write as, because you can see in the pressure coil one, the first one is connected between the phase A, that means A, and the point N dash. So this I can write as Van dash. So to calculate this Van dash, what I am doing, I am applying the KVL in this loop. Which loop I am going? I am applying the KVL in this loop. So how it will go? From point A, I am going to N. This is Van. Then from N to N dash, Vn n dash. So Van dash I can write as Van plus Vn n dash. So that manner I can write. Similarly, Vbn dash can be written as Vbn, voltage of B with respect to N, and voltage of N with respect to N dash. Because between these point, that means Vb and N dash, this is nothing but Vb to N and Vn to N dash. So Vbn plus Vn n dash. Similarly, Vcn with this I can write as Vcn dash is Vcn plus Vn n dash. I am taking it as equation number 1. So if you want to calculate the total instantaneous power measured, that will be sum of the wattmeter readings of these three. So that will be Va n dash into Ia plus Vb n dash Ib plus Vc n dash into Ic. So what I am doing, I am just keeping this equation number 1. That means what is the value of Va n dash, Vb n dash and Vc n dash in this equation number 2. So this will be Va n dash will be Van plus Vn n dash into Ia. This will be Vbn plus Vn n dash into Ib plus Vcn plus Vn n dash into Ic. So this I am separating out. This I can write as Van into Ia. Here I can write Vbn into Ib, Vcn into Ic. Vn n dash is common for all, so that I have separated out. Vn n dash into, here it is Ia, Ib, Ic. Vn n dash into Ia plus Ib plus Ic. Or this I can write as Van Ia, Vbn Ib and Vcn Ic. Now coming to this last term, this last term, it is coming Vn n dash into Ia plus Ib plus Ic. So for this, what I am doing, I am applying the KCL at this node. So this current is Ia, this current is Ic, this current is Ib. Let us apply KCL at a node. At this node, KCL is equal to, KCL indicates the sum of the currents at any node is equal to 0. So what are the three currents? All the three currents are entering only, so that sum will be equal to 0. That means Ia plus Ib plus Ic will be equal to 0. So because of this, it is becoming 0, since the value of at node n, Ia plus Ib plus Ic is equal to 0. So what I am doing, KCL is applied here. So because of this, this becomes equal to 0. So this is nothing but VAN into IA is nothing but instantaneous power in the first, and VBN into IB is instantaneous power in the second circuit, and VCN into IC is nothing but instantaneous power of the third circuit or the third impedance. So that means this indicates the total power that is measured. That means here we can prove that whether you are connecting this common point to some isolated point or you connect this to n, both will give the same reading, because anyway here also you are getting the same thing. So now coming to the delta connected load, because we have to measure the power in each phase, that means I need the current passing through each impedance as well as the power across each of those phases. That means power to measure the voltage across each of these node. So if you are taking for example the wattmeter 1, this wattmeter 1, the current coil will be connected in the circuit of this ZAB, which is connected between node A and B. Similarly, this pressure coil will be connected between nodes A and node B. Similar is the case for second one as well as third one. So here there is a disadvantage. The disadvantage is, as we have to connect the current coil in series with this circuit. So when you can connect it, only if this terminal, this point is accessible to you. That means we should have the access for all the individual points. Only if the 3 points are coming at the output A, B, C, we cannot connect my current coil. We can connect the current coil only if I have the access to each impedance separately. That means each phase separately, then only we can connect the wattmeters. But in practice, if you see any delta connected load, only 3 terminals will come at your input. Only 3 terminals will be available. That means we cannot go for 3-wattmeter method for delta connected loads. For delta connected loads, we have to go for another method that we are going to see. So for delta connected load, what we will do? We will go for a 2-wattmeter method, because in delta connected load, we know total number of conductors are 3. So the minimum number of wattmeters that will be required will be n minus 1. That means 3 minus 1, 2 wattmeters will be required for unbalanced load. It is not the case of balanced load. Balanced load, simple thing is, you can measure the power consumed by any one phase multiplied by 3. Simply you can get it. But unbalanced load case, if you want to measure, minimum number of wattmeters required will be number of conductors minus 1. So 3-phase 3-wire will be 2. 3-phase 4-wire will be minimum 3. Remember this. Okay. So now I am going. So here I have connected 1 wattmeter in phase A, and pressure coil I have connected between phase A and phase B. Similarly, another wattmeter I have connected in phase B, and pressure coil I have connected between phase B and phase C. So in order to understand this concept easily, so what I am assuming, I am taking the current passing through the respective impedances. I am taking as I1, I2, I3, because I have to ultimately, my concern is about whether the power is measured in the respective, because I should get my equation in the form V into V1 into I1, V2 into I2, V3 into I3 in this form. So that's why I'm taking it. So now, because current always we know that it will pass from higher potential to lower potential. So here I am taking the notation for V1. Let us assume this V1 is indicating. That means this side is plus, this side is minus. That means A is plus with respect to B. That means current is passing like this. Here I2 is passing from B to this direction. That means I can tell the direction of voltage is like that. This side plus, this side minus. So this I am taking as V2. Similarly, in this 3, I am assuming this side plus, this side minus. This is equal to V3. So these are the notations of voltages. These are the notations of the currents. So with these basics I am continuing. So before proceeding, let us see one more thing. If I apply the KVL within this loop. So let us apply the KVL within this loop. When you apply the KVL within this loop, because in KVL tells that the sum of the voltages within a particular loop will be equal to 0. That means this indicate this, because you can start from any one point. This will be V1, then V2, V3 because all are in the same direction. You can see they are adding to each other. So this will be V1 plus V2 plus V3. That will be equal to 0. That is KVL. So please remember this. We are going to see this once we go to the derivation. So now I am going to the derivation. Let us see what is the power measured by wattmeter 1. Wattmeter 1, you can see this current coil is connected in this circuit. So what I am doing, I am applying the KCL at this node. I am applying the KCL at this node. Let us go back. Let us calculate the KCL at this node. So here you can see this I3 is entering in this phase. That means here the current is I3. So what is the current? Apply the KCL at this node. Current entering is equal to current leaving. That means this current is nothing but equal to I1 minus I3. So that when you do here the sum of the currents, then that will be equal to, because I1 minus I3 is entering here, I1 is leaving, I3 is reaching here. Okay. Similar is the case, you apply the KCL at this node. Here the current is I1. So what will be this current? This current will be I2 minus I1. So similarly at this node you can calculate, because this is my value of I2. What will be this value? This will be I3 minus I2. These are the currents. So with these basics I am proceeding further. So in the wattmeter 1, the current that is passing is I1 minus I3, and across your pressure coil you can see this side one is connected to this node and this second side one is connected to this node. So what is the voltage that is connected? V3 is connected, but we know that this side is at lower potential compared to this side, because you can see the direction of I3 is passing like this. That means this common point or C is at a higher potential compared to A, or otherwise this V3 I have to take as minus. So that way I am taking minus V3 into current is I1 minus I3. Now coming to the wattmeter 2. In the wattmeter 2, what is the current that is there? I2 minus I1. Applying KCL at this node, I2 minus I1. And what is the voltage? Because you can see the pressure coil, this is connected between this node and this node. Between this node and this node, you can see the voltage is V2. That means I2 is passing like this. That means this is at a higher potential compared to second point. That's why voltage will be positive. That's why it is V2 into I2 minus I1. So total power will be W is equal to, I am taking the sum of the wattmeter readings, W1 plus W2. So this will be minus V3 into I1. Minus into minus become plus. So plus V3 into I3. Similarly, second one will be V2 into I2 minus V2 into I1. I have just arranged it. So now I have rearranged them. So I1 is common for 2. So that's why I have separated that term. Remaining terms I have written V3 I3, V2 I2 that came here. This V3 I1 and V2 I1. So that I have combined. I am taking minus I1 common. This will be V2 plus V3. So we have just seen in this loop, if we apply the KVL, it will be equal to sum of the voltages is equal to 0. You can see arrows are in same direction. So that's why I can tell that applying KVL in the loop, V1 plus V3 plus V2 or V1 plus V2 plus V3, that will be equal to 0. Or otherwise I can tell that V2 plus V3 will be equal to minus V1. V2 plus V3 will be equal to minus V1. So this I am substituting in equation number 1. So this will become minus V1, minus into minus, that become plus I1 V1. Same thing, plus I1 into V1. So this is nothing but P3, this is P2, this is P1. Instantaneous power in the respect to phases or respect to impedances of this load. So we can tell that by using 2 wattmeters itself, we can measure the 3-phase power of the delta connected load. And you can see it is measuring the individual phases values. That means even the load is unbalanced also, it will measure the proper power in this case. So this is the most commonly used method for the case of delta connected load. So now let us see the case of star connected load. So where the star connected load 2 wattmeter method is used. This is used only in the case of 3-phase 3-wire system. You have to remember that. So this is only for 3-phase 3-wire system. We cannot use for 3-phase 4-wire system. Please remember this. So now here again I have connected the wattmeter in such a manner for it is connected in phase A and another phase. So here, as we know that whatever line current is there, that is same as the phase current, but voltages, line voltages and phase voltages are different. So that's why in order to differentiate and avoid the confusion, I am taking the notation as 1, 2, 3. So I am assuming this is Z1, voltage across this one is V1 and the current passing through this is I1. Similarly, this one I am taking Z2, I2 and V2, Z3 and I3. That means if you are taking the wattmeter 1, so current passing through this wattmeter 1 is nothing but current passing in Z1, that is I1. And what is the voltage? Voltage is, it is connected between the point 1 and point 3. That means it is connected between point 1 and 3. I can write it as V13. Or if you are passing like this, that means you apply the KVL in the loop. So V13 I can write as V1. Here you can see we are going in opposite direction if you apply KVL. So minus V3. So I1 into V1 minus V3. Similarly W2. W2 the current passing is I2 and voltage is, we are taking V2 minus V3. When you pass like this in this loop, V2 minus V3. So otherwise W I can write as W1 plus W2. I am taking the sum of these two and then I am simplifying it. It will become V1 I1 plus V2 I2 minus V3 into I1 plus I2. Because V3 is common, you can see here also, here also. So I have combined them. So again, I am just applying the KCL at this node. So at this node you can see 3 currents are entering. One is I1. So I1 is entering here. Here I2 is entering. Here I3 is entering. So at this node, sum of the currents is equal to 0. So that means I1 plus I2 plus I3 is equal to 0, or I1 plus I2 is equal to minus I3. Or you are substituting this one here. So this will become minus I3 into minus V3. Minus into minus become plus. This will be V3 into I3. V1 I1 is power 1. V2 I2 is nothing but power 2. V3 I3 is nothing but power P3. That means it is measuring the power consumed by the individual impedances. That means using just 2 wattmeters, we can measure the power in unbalanced or balanced case in the case of delta star connected load. So let us take the specific cases. So let us assume the load is balanced in the star connection. In that case, 2 wattmeter method can be used to measure both the power factor as well as 3-phase reactive power of the circuit. Let us see how. Because this is valid only in the case of balanced load, remember this. So again I am going back to the connection. What is the meaning of balanced load? The value of Z1 is equal to Z2 is equal to Z3. When impedances are same, then automatically current drawn by that is same, as well as the voltage drop across the impedance. Because voltage drop across the impedance is current multiplied by impedance. As the currents are same, because impedances are same, currents are same, as well as voltages also will be same. So here I am taking the RMS values. Let V1, V2, V3 are the RMS value of the respective phase voltages, and capital I1, I2, I3 are the RMS value of respective phase currents. So as the load is balanced, so Z1 is equal to Z2 is equal to Z3, and I am assuming these phase voltages, because all are equal, I am just assuming that value is equal to V. Similarly, the currents I am taking, I1 is equal to I2 is equal to I3 is equal to some I. And I am assuming my power factor is some cos phi lagging. That means it is lagging behind the voltage by some angle phi. So then the line voltage, because in 3-phase system we know the line voltage will be √3 times of the phase voltage. So I can tell my line voltage between any 2 phases, 1, 3 for example, 2, 3, 1, 2, whatever you take, it will be √3 times of the respective phase voltages. And if you take the line current, because in the case of star, whatever current is passing in line, same thing will pass in the phase also. So that's why I1 is equal to I3 is equal to I3 is equal to I. So let us go to the phasor diagram now. So now let us take the wattmeter 1. What power it will measure? You can see the current passing through wattmeter 1 will be I1. So that means I1 is there. Then if you come to the pressure coil, the pressure coil is connected between the phase 1 and phase 3. That means it is V1, 3. V1, 3. So I am taking V1 as my reference. This is my V1. The current is lagging behind this V1 by some angle phi. That is I1. So now V2 will be lagging behind this V2 by some angle of 120 degrees. That means between any 2 phases, what will be the angle? That angle will be 120 degrees. Same thing is the case here. This also will be equal to 120 degrees. Same thing is the case here. So now I want to calculate V13. How I will calculate V13? V13 is nothing but, if you are going in this loop, this will be V1n minus V3n, because we are going in opposite direction to this one. So that's why I have to take V3 in opposite direction. So V3 I have taken opposite. So when you take 180 degrees opposite, the total angle is 120. So what is happening? This is dividing your total angle into 60 degrees. So this will be 60 degrees and this will be 60 degrees. So now the resultant of V1 and minus V3, that will be equal to V13 because both are having same magnitude. Angle is 60. So resultant will be in the center of these two. That means this angle, whatever this angle is there, this angle will be how much? This angle will be 30 degrees. This angle will be 30 degrees. So let us try to erase this because this creates the confusion. So let us try to draw this one again. This is my value. So what is this angle? This angle is 30 degrees. Okay. This angle will be 30 degrees. So similar is the case. Second wattmeter, if you see, second wattmeter is connected between phase 2 and phase 3. That means we have to calculate V23. V23 is V2 minus V3. That means the resultant of V2 and minus V3. This is V23. Total angle is 60. So what will be this angle? This angle will be 30 degrees. So now let us see what the wattmeter one will measure. Wattmeter one will measure voltage is V13, current is I1, that is current passing in the phase 1, multiplied by cos of the angle between this voltage coil and the current coil. That will be equal to what is the angle between cos of angle between V13 and I1. You can see what is the angle between V13 and I1. This V13 is making an angle of 30 degrees with respect to E1. And I1 is making an angle of 5 with respect to V1. So if you want to measure the angle between V13 and I1 is nothing but 30 minus 5. So that's why root 3 times of Vi into cos of 30 minus 5. Why root 3 times of V? Because we know the line voltage is root 3 times of the phase voltage. That is the reason. Okay. So now proceeding to wattmeter 2. Wattmeter 2 is measuring V23 and current is I2. So what is the angle between V23 and I2? V23 and V2, that angle is 30 and V2 to I2 is 5. So total will be 30 plus 5. That's why it will be root 3 times of V into I into cos 30 plus 5. I hope it is clear. So now total power I can take by taking the sum of W1 plus W2. When I am taking the sum, this will be equal to root 3 times of Vi into cos 30 minus 5 plus root 3 times of Va into cos 30 plus 5. Root 3 times of Vi is common. I have taken common. So this will be cos A plus B plus cos A minus B. That is nothing but equal to 2 cos A cos B. So this will be 2 cos 30 into cos 5. So this will be 2 into, what is cos 30? Root 3 by 2 into cos 5. 2 will cancel out. So this will be root 3 multiplied by root 3. It will become 3 times of V into I into cos 5. So what is 3 into phase voltage into phase current into cos 5? This is nothing but equal to 3 phase power because all the phases are balanced. This is nothing but power measured consumed by any one phase multiplied by 3. That gives my total. That means just by taking the sum of the wattmeter readings, I am getting 3 phase power. Okay, now coming to, I am subtracting these two wattmeter readings, W1 minus W2. So that will be root 3 times of Vi into cos 30 minus 5 minus cos 30 plus 5. Cos A minus B minus cos A plus B is 2 sin A sin B. So this will be 2 sin 30 into sin 5. What is sin 30? Sin 30 is 1 by 2. So 1 by 2 will cancel out. Only sin 5 will remain there. So this equation will become root 3 times of Vi into sin 5. And we know the 3-phase reactive power is 3 times the reactive power consumed by each phase, that is Vi sin 5. Or simply W1 minus W2, if I multiply with root 3, that will give my 3-phase reactive power. That means 3-phase reactive power can be obtained by root 3 times of difference of wattmeter readings. So now what I am doing, I am taking the ratio of W1 minus W2, that means difference of wattmeter readings divided by sum of wattmeter readings. So difference of wattmeter readings, we have just got it as, here you can see equation number 4, root 3 times of Vi sin 5. And we know W1 plus W2 is 3 times of Vi into cos 5, 3 times of power consumed by each phase. So sin 5 by cos 5 will be tan 5, root 3 and 3. This will become 1 by root 3. Vi will cancel. So this will become tan 5 divided by root 3. Or otherwise, we can write tan phi is equal to root 3 will come to this side, root 3 times of W1 minus W2 divided by W1 plus W2. Or otherwise, phi is nothing but tan inverse of this term. Once phi is obtained, from that we can easily calculate the power factor. So the main concept that is required in competitive exams is what is the effect of power factor on wattmeter readings. Here you have to remember all these analysis we are making for balanced load case. So we have seen the power measured by wattmeter 1 is root 3 into phase voltage into phase current into cos 30 minus 5. Or sometimes in some books you will see this as VL cos 30 minus 5, because line voltage is nothing but root 3 times phase voltage. It is one and the same. Please don't confuse. Similarly, W2 will be root 3 times of V phase I phase into cos 30 plus 5. So when I am taking phi is equal to 0, that is unity power factor case, just substitute here phi is equal to 0. This will become root 3 VI cos 30. Second one also root 3 times of VA cos 30. That means both the wattmeters will measure the same magnitude and that to the positive value. So let us see the case when phi is equal to 60 degrees. That means the power factor is equal to 0.5 lagging. So in that equation, root 3 times of VI into cos 30 minus 60. Cos 30 minus 60 will be equal to cos minus 30 or cos 30. What is cos 30? Root 3 by 2. Root 3 into root 3 will become 3 by 2 times of VI. And going to the wattmeter 2 reading, this will be root 3 times of VI into cos of 30 plus 60. Cos 90 will be equal to 0. That means second wattmeter reading will become 0. First wattmeter reading will be indicating the total value. Whatever the value of power consumed at 60 degrees, that will be indicated by this one. Okay. So I hope this is clear. So let us proceed further. So if you are taking the angle between 60 degrees to 90 degrees, if you substitute in that equation, you will observe wattmeter 1 will be positive, whereas wattmeter 2, what is happening initially, wattmeter 2 is same as wattmeter 1 at 0 degrees. By the time we reach 60, it becomes 0. Then it will go in the negative direction. W2 will be negative. Let us see once it reaches 90, what will happen. So once it reaches 90, which is also called a ZPF lag, if you substitute there, it will be root 3 times of VI cos of 30 minus 90. That means cos of minus 60 or nothing but cos 60. What is cos 60? Cos 60 is 1 by 2. So this value becomes root 3 by 2 times of VI. Similarly, W2 will be root 3 times of VI into cos 30 plus 90. So cos 90 plus theta will be minus sin theta. So minus sin 30. Or this will be sin 30 is 1 by 2. This will become minus root 3 by 2 into VI. You can see both are having same magnitude but having opposite sign. That means at ZPF lag, both the wattmeters reads the same value but in the opposite direction. So, but here the problem will come. Because once the angle is crossing 60 degrees, we are seeing that W2 meter reading is showing negative. But practically if you take in your lab, can the wattmeter show the reading in opposite direction? Because minimum reading will be 0. It cannot go beyond that. So in that case, if the meter reading is crossing the 0 going to the negative side, that means up to the extreme bottom. So in that case, that indicates the power is negative. So negative power, how you can measure with the wattmeter? Reverse any two terminals. That means either reverse the terminals of current coil or pressure coil terminals. If you reverse them, then it will show the positive reading. You have to note it down as a negative value. I am repeating again. If the wattmeter reading is going below less than the 0, that indicates the power is actually negative. But it cannot measure the negative power because wattmeter cannot go to negative side. So you have to reverse the either current coil terminals or pressure coil terminals of that particular wattmeter. Then that gives the reading in the positive direction. But while noting down, you have to take it as a negative value. In that manner, you have to take care in the lab. So I am just making the summarization what you have studied till now. So when phi is equal to 0 degrees, which is called as unity power factor, W1 will be equal to W2. Both are positive. For 30 degrees, we have not calculated because you can substitute and calculate. 30 degrees means 0.866 lag. In that case, you will get W1 is equal to 2 times of W2. Here what is happening? W1 is increasing, W2 is decreasing. By the time you reach 60 degrees, W1 will read the total power, W2 will be equal to 0. So after that, what will be there? W2 will start indicating the negative value. That means as you reach ZPF lag, one will be positive, another one will be negative, both having same magnitude. That's why if you take the sum, it will be equal to 0. I hope that how the power is measured in the three-phase circuit using 3-wattmeter and 2-wattmeter method, which method is used in which particular case is completely clear to you. So if you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you. Thank you very much.